Okay, so I will quickly explain who we are and why we did all this. Then I will give a quick tour of the ZeroRPC, or framework to do RPC with ZeroMQ. So a quick tour of the features, and then I will give some details about how we implemented it. So why did we implement a full-blown RPC layer on top of ZeroMQ? Well, because we're running a PaaS, so we deploy, monitor, scale, and all that jazz apps in the cloud. And this involves many moving parts, many components, load balancers, code stores, and on a very large distributed cluster. Just to give you a really rough overview, this is approximately what our platform looks like. So all the gray boxes are different services talking to each other. And the red boxes are servers that are actually present in hundreds of instances for the nodes on the right and tens of instances for those on the left. So our requirements were basically, we wanted to be able to expose Python code running somewhere and to call it from somewhere else. So this is pretty basic, but we wanted to avoid to have any modification to existing code. So I want to be able, if I have a Python module foo and I import it and I can call a function, I want to be able to do the same thing transparently if the code is running remotely. So far it's pretty basic. We wanted to have something that would document by itself, if possible, because we didn't want to maintain a separate documentation. Well, not only because we're just a bunch of lazy folks, but also because manual documentation tends to be out of date all the time. And if you can't trust the doc because you're wondering if it's out of date or maybe not, well, then it's better to just not have any doc at all. So ideally, we wanted something that would be able to use the doc strings and the introspection features of Python. We had a couple of more difficult requirements. We wanted to be able to propagate exceptions. So if I'm calling remote code and it's throwing some exception, I want to see that exception and not some obscure remote exception that make no sense. We wanted to be language agnostic because even if we have a mostly Python code base, we wanted to be able at some point to plug some maybe Node.js, Ruby, or Java stuff, who knows. We wanted to have the ability to be brokerless, highly available, fast, and to support exotic topologies. So what does that mean? Brokerless means that we don't want to have to fire up some special server each time we want just to have a small RPC call running. Highly available, well, we just want things to not break if just one process or server goes down. Fast, because we want to use that for logging and for metrics, which both have like thousands or tens of thousands of messages per second. And fan-in and fan-out topologies means, for instance, when we update some HTTP virtual configuration, it has to propagate to a large number of load balancers. But we don't necessarily want to have all those features at the same time. So for instance, it's okay to require a broker when you want to be both fast and have fan-in and fan-out. We don't want to have everything for the same service. So it's okay if not all those requirements can be met together. Also, we wanted to be able to trace and profile nested calls. So if I have a service calling another one, calling a third one, calling yet another, if something takes a long time or if there is an exception, I want to know where is the exception and I want to know what is taking so long. So why did we not use something else? So we considered using HTTP and also some MQP-based solutions like RabbitMQ, but both had the problem of having a significant overheads for some of our use cases, like the metrics with thousands of messages per second. And also, when using HTTP, a lot of those use cases require some extra work. So for instance, all the problems with real-time streaming updates can be solved with HTTP and WebSockets, but when you're doing WebSockets, you could as well be doing plain TCP, and there is really no point of with using HTTP in the first place. So we decided to reinvent our own wheel. And we named it ZeroRPC because it's RPC based on ZeroMQ. So we use ZeroMQ. We decided to use messageback for serialization. It supports everything we needed. So if all of those requirements sound good to you, please use it. And we came up with multiple implementations. We started with something simple in the beginning, which became more and more involved with time. And so it's in Python. And at some point, we came up with a new implementation from the ground up. And this new implementation is now on GitHub, and it's open source. And we encourage people to use and abuse it. We also have a Node.js implementation, but it only supports a partial set of the features. So it's not really for public use yet. So quick tour of what we can do with ZeroRPC. We can expose any Python code without modifying it. So for instance, here we're exposing, there is a little tool provided with ZeroRPC client, that allows to start client servers and all kind of stuff. So here we expose the URL lib standard Python module. Just this command will make it listen on port TCP1234. Then we can call it with the command line client, which is mainly used for debugging and poking purposes. And we can call it from Python code, just like we promised. So we connect, and once we are connected, we have an object which behaves just like the normal URL lib module. It can expose modules, classes, anything which has a list of callables. We can do introspection, so we can list the methods, we can see the signatures, so arguments and argument names, and docstrings. We can see exceptions, so if I try to call the quote plus function without supplying the argument, I will get a traceback with, well, a bunch of stuff, but at the end, I can see my normal plain old type error, reminding me that I forgot to add one argument. It has load balancing, so the load balancing actually requires a tiny broker. So we named that a hub. So you fire up the hub, which is, it just requires 3 lines of YAML. And then you connect some workers to the hub, and then you connect to the hub to make your queries, and that's about it. If you need high availability, we will again use a tiny broker, which is this time HAProxy. So HAProxy is a well-known load balancer, mainly for TCP and HTTP. And with the really super simple configuration shown here, we have something to provide high availability for ZeroRPC services. There is nothing to do in the code. Actually, there is nothing to do in our code neither, because ZeroMQ handles everything for us, reconnection and all that stuff. Now, a non-example. So an example, things that we did in the beginning and then we realized we were all wrong. So I would advise you not to try that. So ZeroMQ has support for pubsub topologies, so to broadcast information or to collect information to a central place. But it has issues, not with ZeroMQ itself, just because in the beginning we completely missed the point of pubsub. Pubsub is not for reliable streaming of information. If you disconnect and reconnect to the thing that is publishing information, you will lose some updates. So sometimes it's fine. For instance, if it's some metrics, if you send every 10 seconds the RAM or CPU usage, you don't care if you miss a few data points. Now, if it's some logs or some RPC call, if you lose it, consequences can be worse. So instead of using pubsub, we ended up implementing something special with ZeroRPC called streaming, and I will give some details about that. So streaming, that's when you need to send, for instance, a big bunch of data. For instance, when we need to retrieve all the CPU usage for a given application over the last week, this can be a lot of data, because with a lot of data points. And initially, the first implementation was really bad. It was building a huge list of data points. It was converting them with messageback, sending them over the wire as one big bulk of data, and at the other end, you would have to do everything in reverse. So the streaming mode that we implemented allows you, in your code, to return an iterator, and then the client side When invoking the function, we'll get an iterator as well. And when you fetch the data from the iterator, it automatically, behind the scenes, fetches data from the server. So that's good for all kind of applications. So big messages or constant stream of smaller messages, and also long polling. So when you want to get a notification when something happens. We have tracing. So this, unfortunately, is not yet in the public repository because our implementation is tied with a lot of our internal components, but we are working on this to open source it as well. So what does it mean, tracing? This is an example when someone has an app on .cloud and he's adding a domain name to it. So there is a command line, it does .cloud, alias, add my app, and then the domain name. So we can see that this is actually an HTTP call going over an HTTP endpoint. So the trace begins at some uWSGI worker, then it goes to a zero worker. There is some tracking to register what the users are doing for statistical purposes. And then it goes through all the components of our platform, and we can see the timing information. So we can, if this call takes too long, we can see exactly which part of the call took so long. So let's see how we implemented all that stuff. So the following part will be useful if you want to use ZeroRPC and wonder what's under the hood, or if you are excited about the idea of forking this on GitHub and doing some cool stuff with it, or if you want to reinvent your own wheel because you have different requirements, but you preferably want to avoid shooting yourselves in the foot just like we did. Or just if you're curious about distributed systems. So why did we use ZeroMQ? Because ZeroMQ is just like plain old TCP and UDP sockets, but much better. So for instance, it handles connections for us. Normally, if you have a TCP server and you connect to it, if the server is actually not running, the client will get a connection refused error. With ZeroMQ, the client will just wait patiently for the servers to show up. ZeroMQ is able to use, well, there are plenty of other cool features in ZeroMQ, not just that one. So ZeroMQ can work over regular TCP. So there is no low-level custom network protocol or something like that. But if you need it for really high-performance applications, so that's like tens or hundreds of millions of messages per second, there are IPC and in-proc transports, which are respectively local to the machine and local to the process. And it supports different topologies, so request response, pubsub, push-pull to do some load balancing. And the good thing is, if you want to start hacking with ZeroMQ, even if you're not interested by ZeroRPC, you can just pip install PyZeroMQ static, and it will take care of everything. It will install the ZeroMQ libraries and some of its dependencies, and it will work. Big thanks to Brandon Craig Rhodes, who make the PyZeroMQ static package, because this saved us countless hatches. So, serialization, we use messageback. So why messageback and why not JSON, Bison, XML, YAML? Just because we did some really simple tests and we found that messageback was faster and more efficient space-wise. So depending on the test, it could be between 20 and 50 times faster and sometimes even better. And the output, the byte stream, was at least twice smaller. Same thing, if you are looking for something to serialize stuff, well, you can pip install messageback Python and play with it as well. So the wire format, so what does a request and a response look like with ZeroRPC? We decided that it would be something like this, with some headers, the name of the method that you want to call, and the list of arguments. Nothing really fancy. The headers is completely optional. In the beginning, we didn't even have the headers, and then we thought, oh, what about protocol extensions? Let's put some headers over there. And we use it in our in-house implementation for the tracing stuff. The args are just, well, the list of arguments. We don't support keywords arguments. because we wanted to have something that would work with languages that would not support keywords arguments. So that's the only reason why. And the response messages are exactly the same, except that the method name is just something saying if the call went well, if it was an error, or if it's a stream, then there is more data coming after that. And the return value, it takes the place of the arguments. Timeouts. Some of you might have noticed that I mentioned that if you connect with a client with ZeroMQ and the server is not there, the client will wait forever, which in some cases might not be what you want. So we implemented timeouts. So if you send a request and nothing happens after like 30 seconds, you just decide that the request is dead. But in some cases, it's wrong. Sometimes it's just that you're doing a call that needs more than 30 seconds. So the improved implementation, the one that is on GitHub, has something better because the server will send heartbeats. So the client will know, okay, the server is still working on that, and the client will wait. Introspection. This was actually quite easy. We just, when you expose something like the URL lib module as shown in the example in the beginning, we add a few extra functions, ZeroRPC list, name, help, args, that will peek inside the module and give you the list of functions and the arguments and docstrings of the functions. That was quite easy, and that was super useful when we have a new hire and we just drop it in front of the keyboard and we give him the keys to the ZeroRPC stuff, and we tell him, okay, now poke around, look at the list of services, look at the method in them, look at the docstrings, and we found out that it was really easy to find your way in very large distributed systems with something like that. Naming. So right now in the version that we have published on GitHub, you have to specify the host and port that you want to connect to, which is not so great. In-house, we have something using just a flat YAML file, but we were ashamed of this, so we didn't want to publish it on GitHub. But we are considering to have something like DNS lookups using a combination of maybe SRV and TXT records. We didn't decide yet exactly what we want to use, because internally we will probably still be using this flat file, because even if it's a shame, at least it doesn't rely on anything external. So even if the DNS goes down, the ZeroRPC calls will go on. Security, well, bad news. There is absolutely no security in that stuff, because ZeroMQ assumes that you're running on a trusted internal private network. Since this is not always true, we have a few recipes to run that in the wild on public TCP ports. The easiest solution is to add SSL with stunnel. So it's maybe a 5 or 6 configuration file for stunnel, just to wrap the ZeroMQ connections within SSL. We have a prototype for authentication that adds MD5 or SHA hashes of the requests and responses to make sure that they are not tampered with in flight, and to make sure that only authorized people can actually make RPC calls, but it's not completely ready for production yet. Also, we have HTTP ZeroRPC gateway that our API actually uses. So as I mentioned, when someone does a .cloud command, the command line will actually do some HTTP requests, and those HTTP requests are immediately translated into RPC calls. Well, after an authorization round trip, but then there is a clean mapping of the calls between ZeroRPC and HTTP. Tracing. So tracing is not published yet because it uses a lot of our internal libraries and stuff. So when we started to pull it out to include it into the public repository, we ended up pulling our entire code base. But we are currently working on something to open source the tracing system. So the tracing system, the interesting stuff is that it actually only took 1 day for one of our engineers to craft the tracing system with what we already had. And he added a lot of cool features like real-time graphs of latency, the ability to take that boring line per line trace and do a nice graph with it, because sometimes some calls will fan out, so you do one call to multiple machines and one of them will respond. So in that case, it makes sense to have a real graph instead of just a trace back line by line. And also the tracer can send exceptions to Airbrake, Sentry, or services like that. So when you have an exception in your ZeroRPC stuff, you get alerts on your favorite exception monitoring tool. So how does it work? The grand plan is that each time there is a call or a response, we send some information to a central place and we index it with a trace ID, and then we can retrieve all those small trace elements, let's name that tracelets, and we can see all the calls that were involved in one complex call. So this trace ID, each call has a trace ID, because when you're doing a call, if you don't have yet a trace ID, you make one up. And if you're within a call already and you make a subcall to a different service, you will reuse the same trace ID. And it's stored in a local context, a bit like a thread local storage. And so the trace ID will go along with the call during the whole lifetime of the call. Then those small trace elements will contain the trace ID, the call name, so just the function name, the name of the current process, so is this the vhost service or is this some NAT service or something else. It also contains the host name, so you can know where the thing is running, and a timestamp. And it will send all that stuff to a central place. This central place is actually a Redis key value store, so it keeps everything in RAM because it has to be fast, because it's receiving a constant stream of traces all the time. It's in RAM, so it's not persistent, but we don't care because this is mostly for debugging stuff, so we really don't mind losing the trace of the calls that we did last week. Just for information, the whole platform is generating about 16 gigs of trace every day. So we could keep that, but we decided not to because we really don't need them. So we use some Redis features to make this component really fast, efficient. Everything is like a big O of one, so great stuff. Actually, we don't talk directly to Redis. We talk to a service that itself talks to Redis, and that service in the middle will trigger Airbrake or Sentry and that kind of notification. So the first implementation that we did was Synchronous. This means that if you have a call that takes a very long time, the whole service will block. So for instance, we had a call to spin up new servers, new EC2 instances, and sometimes this takes a while. So when you would be spinning up a server, you wouldn't be able to do something else with or EC2 bridge during the same time. So the first solution was, well, let's do some load balancing as explained in the beginning. So we put this hub, we have multiple workers, and we dispatch the request on the workers. The problem is when you have really, really, really long calls, eventually you will run out of workers. This is not a problem specific to ZeroRPC. We have the same time with web apps using, well, WSGI web apps have the same problem. You have to spin up multiple WSGI workers, and if all your WSGI workers are busy, well, the app just stops responding. So at first, we thought, well, let's do just like Node.js. Let's have some asynchronous event all over the place. So when you need to do something, you send the request and you tell, okay, once the request is done, send me the result to some other place. So just like callbacks in Node.js or in asynchronous loops like Twisted and all the like. We tried, the result wasn't pretty. And we learned that, well, trying to do that, it can work, but it requires a lot of care to make sure that, notably, one of the big problems was the problem of trees falling in the forest with no one to hear them, which means you're doing a call and you're telling, well, once you have the result of this call, please call this other function. If something goes wrong, the function is not called, and the whole workflow that we are following just stops, because at some point, someone didn't call the next thing to do. So maybe it could have worked if we had been careful programmers, or if we had some better features, or maybe actually from a theoretical point of view, if we had some kind of something to make sure that we don't lose the state of those calls. So when we would start a call, it would monitor them, and if they happen to be lost in space, it would start them again. But this was too complicated. So we decided to use GEvent, which is a really cool asynchronous framework using coroutines. So you're still writing synchronous code. You're not sending callbacks and events and stuff like that. And it works. The code won't have to fork, it won't have to use threads, and, well, I'm not saying that you won't have any problem, but it was way better than what we had before. So GEvent turns your whole code base into something fully asynchronous. It achieves this by replacing every blocking call in the standard Python library with a non-blocking version. But I think there is a talk about GEvents just after mine, so you will certainly have some details. And this was the real solution to our problem. And the good news is that the version that we have on GitHub has this GEvent stuff in it. So you can expose some Python code that takes time to run, and it won't block just because there is one long function call running. So, the code. We published the repository just this morning, after late adjustments and everything. It works. We use it in production, and it can normally be installed just by pip installing it directly from GitHub. It will probably be on PyPy shortly, that's about it. So it has the ZeroPC module I was talking about. It has this small command line tool to expose modules and to see what they're doing. It propagates exceptions. It has the integration with GEvent. But now what it doesn't have is tracing, naming, stuff to make nice pubsub and push-pull integration, and authentication. But the good news is that we have implementations for all those patterns in our code base, and we are willing to open source them progressively, so expect to see more in that area. That's it. Do you have any questions?
I have a few questions. I've got a couple, so tell me to get off the stage if I'm taking up too much time. So what do you do if the function signature changes on a remote host? How do you deal with those changes?
If it changed during, so if a function signature on the server changes, if it's changed during the call, or if at some point you release a new version of the service with a different signature? So the thing is that it's completely dynamic. So if you make a client code with, let's say, 2 arguments, but actually the new implementation has 3 arguments, you will get an exception telling you that you don't have enough arguments. Well, just like when you change some normal Python code in a library and you don't change the code using the library.
Have you developed any best practices internally for dealing with that?
So do we have best practice to deal with changes in APIs? We are working on that. For now, our guidelines are don't make any incompatible changes. So if you extend the call, add optional arguments with sensible defaults, And if it's something different, just add a call. So that's why some of our services have like 6 or 7 calls that look like the same, but each has a really different, slightly different behavior.
That sounds like the way to go. Does ZeroMQ still throw asserts when the unexpected happens?
Does ZeroMQ still, sorry, I didn't-
Does ZeroMQ have assertions in the library that cause the program to crash still? Because I know that was a problem earlier.
If it has, sorry, I didn't understand.
No? Okay. Thank you. One last question. What do you do if pool membership changes, i.e. you add a server to the RPC pool? Do you have to update the HA proxy config every time, or do you have some sort of automated tool?
So what do we do if we add or remove workers in a HA availability setup? So actually, the infrastructure looks like hubs. Workers connect to hubs, so we can add and remove workers without reconfiguring anything. And the only thing that's hard-coded within HA proxy, the location of 2 hubs.
Got it. Thank you.
Hi. First of all, I just want to say thank you for making this open source and releasing this as open source, because it's tools like this that make Python so great, right? So I guess thank you on behalf of Python for that.
Thanks.
I guess my question is, how do you determine worker utilization? So you have all of these different workers doing things that are kind of doing the same sort of class. How do you figure out worker utilization?
So how do we figure out how many workers are required and that kind of stuff? So back in the days before the GEvent implementation, we had a kind of dynamic worker queue, a little bit like the Apache mechanism that spins up and down workers. It worked so-and-so, and it could also examine the queue length and stuff like that, but it didn't solve everything, because at some point you would just end up with hundreds of workers and all busy within something. So the GEvent implementation completely removed the worker issue. Actually, there were some cases where we would be using some library that would be compatible with GEvent. So in that case, we would be back to the plain old workers. But there are not too many of them, so we were able to figure it out.
I was just wondering what kind of overlap there is with a project like Twisted, because it seems like this solves some similar issues in terms of asynchronous and distributing things over a network.
So the relationship between this and Twisted, for instance, I think instead of using GEvent, we probably could have used Twisted, but we were completely excited about GEvent because it would allow us to continue to write normal code, like synchronous code, without twisting our mind around asynchronous patterns. I think it would totally make sense to have, well, just like there is ZeroMQ GEvent, to have ZeroMQ Twisted, and then to have zRPC Twisted to plug RPC calls within a Twisted event loop.
Hello. I have a question about exceptions. How are exceptions handled in a cross-language manner? So how do you get properties off an exception object, and what do they look like over the wire?
So how do we handle exceptions across language barriers, and how do we send them on the wire? So across language barriers, we don't. Actually, as I said, we have a preliminary Node.js implementation that only has a partial subset, and it doesn't deal with exceptions very well. We tried to convince some Java shops to use ZeroRPC and to see where it would lead us, but so far our attempts were unsuccessful. But that's a completely open issue. The way, so how we send them over the wire, right now I think it's semi-structured, so it's like we're not trying to pickle exceptions and do any fancy stuff like that. At the beginning, it was just a big bunch of text, and right now I think it's a little bit better because it's a list with the traceback, but it's something like a hack for now. So we think that the first other people to use this with different programming language will probably have to figure this out for us. But yeah, we will probably at some point write some kind of preliminary spec to help other implementations.
How do you do offline development, and how do you test against your remote servers?
So how do we do offline development? So like...
Yeah, like you're on a plane and you're adding a new feature, but you can't talk to any of your services.
Oh, so if I'm on a plane and I want to work on this, well, in our specific case, we just happen to have a virtual machine with a staging version of the whole platform with all the services running in it. And actually, in that case, ZeroRPC helped a little bit because the naming system that we had, this ugly YAML file of shame, helped us to have those different versions: production, staging, development, virtual machine. But we don't have anything to so you can make calls and have some magic happen. Well, actually, if you make a RPC call, since it's ZeroMQ, as soon as you have network connectivity again, the call will make it to the server and you will get the reply. But there is nothing else than just, well, you can have mockups for your services and stuff like that, but we really don't try to address that. Thank you.